thermodynamic stability of the complexes. Now we'll discuss the solvent effects. What is the role of the solvent in supramolecular chemistry? So particularly when host and guest molecules they will associate, they will arise the equilibrium process. This is called association equilibrium. So definitely the association equilibria in case of solvent molecules it is not stable because the solvent molecules throughout the complex or through in a particular complex or in a particular pot they are not stable. They were just moving from one complex to another. So there are dissolution and their binding process. Now we'll discuss about the dissolution and binding process of the solvent molecules. So before binding of the guest and host molecules, they initially solvated. Both the host molecule and guest molecules, they both will solvated initially. You can see here the structure, the circle. This is the host structure, and these are the molecules of the solvent. So these three atomic molecules, particularly you can denote it as just like a water molecule, and the bigger version is the oxygen, and these two small balls are the hydrogen atoms. And the complete circle, this is a host molecule. So this host molecule initially solvated. This is called solvated host molecule. And this part we can say solvated guest molecule. And this the inner dark circle, this one. This will be the guest molecule, and these are the solvent molecules. So you can see here, this is a solvated guest molecule. So when both solvated host and solvated guest, they will combine, they will form a structure like that. So in second process, before combination, both will be solvated, and when the binding occurs, so in cost of binding, they will sometimes lose some enthalpy cost. That means mostly the bond forming reactions are the exothermic reactions. When a bond will form, they will lose a huge amount of energy. So when the solvent host and solvent guest interaction occurs, there may be two processes or there may be two possible processes. In one process, it can cost the enthalpic loss also. In some processes, it can also gain some enthalpy also. Okay, and the another important factor is that entropy. So enthalpy and entropy both will govern the feasibility of reactions. So after binding, what happens? So after binding, you can see here the total complete circle. This is the host, and the dark circle. This is the guest, and the solvent molecules they will move away from the host ghost complex or host guest complex. You can see here. So when the solvent molecules they will move away from the host guest complex, they will be little bit more free. That means we can say when the solvent molecules they will get separated from host and guest, they will make a random motion outside the complex environment. So due to their random motion or due to their disorderness or due to the random motion of the solvent molecules, the entropy inside the system it will increases. But initially the solvent molecules just are, we can say these are stabilized by making a complex with host or we can say guest. But here the solvent molecules they will just move outside the host host guest environment, and they make a increase in energy, sorry, make an increase in entropy throughout the system. So when there will be increase in entropy, definitely the gives free energy value it will decreases, and the decrease in green energy makes the process more feasible. You can see here the complex. Okay, so initially it is only sorted post guest, which on dissolution gives a complex, and the final complex is still solvated. But here, most of the water molecules they will move throughout from the host guest environment, but some few solvent still they will make in contact with the complex. Okay, but majority of the solvent molecules they will go outside from this post gust environment, and the final complex is still solvated, but overall there are more free from solvent molecules presence, hence increasing the entropy of the system. So the product here, the solvated host and the solvated guest they will interact, they will form a host ghost guest complex with little bit solvent molecules along with some three more number of solvated molecules. So these three solvated molecules, they will particularly increase the entropy of the system. So if the entropy of the system will increases, then the feasibility of the reaction is more possible. So here we can say the host-guest interaction, it leads to a formation of a stable complex. And this process, we can say this is a equilibrium process. That means it go in forward direction also. And in sometimes if the solvent molecules again it will make an interaction, they will go backward direction also. Okay. But the forward direction, it will support towards the feasibility of the process. Next, some few other factors we will discuss. Enthalpy. So energy input needed to break host solvent and guest solvent interaction. So here for interaction of this guest and host, initially we need to separate the solvent molecules from the host and the solvent molecules from the guest. That means we need a entropy cost or we need a entropy input initially to make them separated from the solvated molecules. And the entropy, so the entropy here arises, due to these three solvated molecules. Okay, so the solvent can either stabilize or destabilize the host-guest complex, but there is a role of solvent polarity. Particularly, if the solvent polarity will be more, or I can say if there will be more polar solvent, then definitely they will make a strong interaction with the host molecule and the guest molecule. So initially, we will check what happens if you take particularly the polar solvent or if you take a non-polar solvent. So when you are taking a polar solvent, actually strongly solvated charge species which hinder the binding. That means to formation of a good or stable guest host complex, we need to easily separate the solvent molecules from the host and guest. So if initially the solvent molecules will be more polar, it will make a strong bond with the host and the guest complex. So we need to take a less polar complex or a less polar solvent that will make a little weaker interaction with the host and guest molecules. So if you take a polar solvent, it will be very difficult to break the bond between the solvent and host and the solvent and the guest. So particularly, you can say polar solvent, you can take a DMSO competes by donating and accepting hydrogen bonds and lone pairs. So if you take polar solvent, they will make sometimes slightly electrostatic interaction. Sometimes they can make also hydrogen bonding. Or sometimes if you take particularly DMSO, particularly the oxygen atom on DMSO, they will donate an electron pair to the host and guest molecule and make a stronger interaction within themselves. Okay. If you take less polar solvent particularly, so weaker competition leads to a stronger host-guest binding. That means if you take a less polar solvent, it will make a weaker interaction with the host and guest. So to form a host and guest complex, it will be easier to separate the solvent molecules. If you take if you take the less polar solvents, so the less polarity of the solvent, it will be a barrier for the formation of host-guest complex. So if you take a less polar solvent, so the complex formation it will be very easy. So we can conclude it by this sentence that is written on the end of the slide. You can see here. Thus, it can be said that if the binding constant is too high to measure, a more polar solvent can be used to reduce the apparent binding strength. Here we should note a kinetic stable complex or we can note a thermodynamic stable complex. So particularly the thermodynamic stability, it follows a lower free energy pathway. What I, but it during the formation of a thermodynamic stable complex, the process it may be slow or it may take a larger time due to its high activation energy. But kinetic products they will form easily within a less time. We can say just like an example, if you take a bulky ligand, they can bind quickly with the metal complex. If you take a smaller ligand, they can also bind with the metal complex, but it will take more time. So it may take more time. Smaller ligands it may take more times, but finally they will form a stable complex, which is more stable than the kinetic product. Okay. So when I am saying a kinetic product, that means these products forms in a faster way or within a few seconds or within a small lifetime. Okay. So there is a barrier we can say if the time period is more than half minute, then we can say this will be a thermodynamic product. If the half life period will be less than half minute, then it will be a kinetic product. Okay, so there are some few important questions. You can see here the terminal questions, given examples of the Gillette effect and the cooperativity. You can see the answers here in the last. So cooperative effect particularly follows in hemoglobin. You can check your materials in BSc hemoglobin. There will be, that means one hemoglobin molecule. It is just like a tetramer. So one hemoglobin, it can combine four oxygen molecules. If it will combine the first oxygen initially, they can cooperate or they can make a favorable condition for the other oxygen molecules to bind with the hemoglobin complex. This is a positive cooperative effect. So when saying a cooperative effect, that means that is a positive effect that supports the binding of guest and host. So another cooperative effect we can say the metal ligand complexes, particularly the stellate ligands. Stellate ligands means those are forming the cyclic complex after combination or after making coordination bond with a metal complex. So we cannot say monodental ligands; they are forming the stellate ligands. So for stellate ligands, we need to take a chain type compound or chain type ligand that can form a cycle with a metal complex. So particularly monodental ligands never form more stable complex. But other types ligands, we can say particularly bidental ligands, tridental ligands, or tetradental ligands, or we can say in a formal way, polydental ligands, they have chances to form a cyclic complex with a metal. Okay. And the second terminal question, you can see what are the some factors that affect the chillet effect. Discuss about some factors that will affect this chillet effect. We can see here the first thing is the ligand structure. So ligand structure is basically more important. What you told in and just earlier. So particularly the ligand structure is very important. You cannot take a monodental ligand for this chillet complex. Okay. Second thing is the ring size. Previously I told you uh, that doesn't mean any type of cycle or any type of ring that will favor stability to the complex. If you take three member ring, quite okay, but it is a strain ring. If you take in place of three member ring, if you are taking the four member of the ring, definitely also the strain is exist. The strain is little bit less, but it will still exist. If you take five member ring, I can say strain is very less, very less, and it is the most stable complex forming with a metal complex. So in place of five, again if you choose six memory, definitely the stability is there. There is very less strain, but it will be little bit flexible nature. It will be little bit flexible nature. So for complex stability, another factor is that there must be a planar complex. If it will deviate from the planar, then definitely there will be increase in or there will be chance of decrease in stability. Okay, so the planarity should be maintained properly inside the complex. So for ring size, I can say or concluded just like that. If it will forming five or six member ring, that means the stability is good. And then another factor is that solvent effects. So the solvent effects that can influence the interaction between the ligand, metal ion, and solvent molecules. I told previously, if you can take polar solvent, you can take non-polar solvents. If you are taking non-polar solvents, then there will be chance of definitely forming of a strong, stable complex. And another factor is that metal ion property. So you can see in crown ether complex, sodium ions, potassium ions, and cesium ions that will be trapped inside the crown ether complex. So there will be no issue. But if you increase this the positive charge density of the metal, what happens particularly? If you increase just the positive charge density of the metal, they can bind strongly. The similar oxygen atoms, they can bind more strongly because the overall charge density here increases. So when the overall charge density increases, the binding affinity or binding tendency also increases. Okay. So you can check here the other questions also. Discuss how temperature can shift the balance between kinetic and thermodynamic control in supramolecular complex formation. You know the lower temperature always favors the kinetic products, and the higher temperature it always favors the thermodynamically controlled products. Okay. So the question number 4 here, a host molecule H can bind to guest molecules G1 and G2. First, the host and G1 forms quickly, but the complex dissociates within a minute. Then the host and guest molecules form slowly, but the complex is extremely stable. Can anyone say the first one will be the kinetic product and it will be the thermodynamic product? Anyone? Host and guest H plus G1 forms quickly, but the complex dissociates within a minute. Out of the two products, which one will be kinetically controlled and which one will be thermodynamically controlled? Can anyone? So here the product which forms earlier or it takes very less time, definitely the upper one will be the kinetic control and the second one will be the thermodynamically controlled. You can check here the answers also. Okay, they are not mentioned particularly the answers. Okay, what you can discuss or you can write on from your material also they mentioned. Okay, so the first one will be kinetic control and second one will be the thermodynamical control. Why are five member select rings are most stable? I already mentioned here. Okay, in five member rings there will be very less strain, and this is here also the flexibility amount is also very less. So the two factors when you are comparing the stability of select ring, you should check what is the strain of the ring and what is the flexibility of the ring. If the strain also more, the stability also less. If the flexibility also more, and the stability is also less. So we need to check in which complex both the strain and the flexibility it is minimal. So in five member ring, the strain is also minimal and the flexibility is also minimal. Okay, and these things we will also discuss initially. What's the role of the hydrogen bonding? What's chemical complementary? What is gives free energy? Del G equal to del H minus T del S. And so how cooperative can be quantified? What is cooperative effect in binding in hemoglobin? And how hydrophobic effects play a role in complementary during post and guest interaction. So you need to discuss. So you need to remember the answer of all the terminal questions. Okay. So next we'll discuss about some other thing. Next we'll discuss about the pre-organization methods or the molecular receptors. Okay. So molecular receptors are special designed molecules that can selectively bind to specific guest molecules through non-covalent interactions. So the molecular receptors are nothing but these are particularly the host molecules. We are designing a good host molecules that can have a good selectivity towards binding the gas species. So the design or efficiency depend upon the structural pre-organization. That means sometimes you need to modify or modulate the structure of molecular receptor according to the guest molecule that can easily interact with themselves. So the design or efficiency that can depend upon some few factors. So first one will be the structural pre-organization, their enthalpic stabilization, entropy contribution. We need to look after these factors also. After binding, they must have released a good amount of enthalpy, or the entropy contribution should be positive, and they must make a structural fit in between the guest and host. So these are three very important factors before design a particular molecular receptor. Okay. So for design of a molecular receptor, we need to check what happens particularly, or we understand. What is particularly the host-guest concept that contribute towards the molecular receptor. So when a larger molecule, we can consider it just like a host, envelopes or accommodates a smaller molecule like guest, a host-guest complex is initially formed. So Donald Trump said that you need to remember this definition. Any question? Am I audible?
Sir,
Okay. So this definition we need to remember also. And is very important. The host component is defined as an organic molecule or an whose binding sites converts in the complex. That means a binding site is any region of host or guest that is complementary in size, it must have complementary in geometry, or it must have chemical nature to interact with the other partner. So chemical nature means nothing but this is simply the non-covalent interactions we discussed in the first class. Dipole-dipole interaction, ion-ion interaction, dipole-induced interaction, hydrogen bonding, these are the chemical natures. Or I can say these are the chemical interactions. So these three things are also necessary. What is these things? Their size, geometry, and the chemical natures. So there are different types of supramolecular complexes. We can overall distributed or the supramolecular complexes into three types. One will be the post-guest complex, and another will be lattice inclusion complex or clathrates, or another will be self-assembly complexes. So you need to check here one by one what are the post-guest complex. You can see here initially there is small molecules. They can make a synthetic process. They can undergo a synthetic process. They can form a cyclic host like that. So during the formation of host, the small units they can contribute or they can participate or they can bind themselves through covalent bonding. There will be no issue. But the host guest interaction it will be always just like a non-covalent interactions. So the small units initially they will combine with themselves through covalent interactions and they are forming a cyclic complex like that. In this larger cyclic complex, I can say this is a host complex. And with the host complex, this guest molecule, this small guest molecule, they will interact and they will form a structure like that. They will form a host guest complex like that. Okay, you can see here this guest molecule is trapped inside the host complex and they are making a non-covalent interaction with the core end of the host complex. Okay, we can simply understood or consider just like a hemoglobin molecule. These are the hemoglobin molecules, these four tips, these are the four pyrroles. This is the iron atom, this is trapped inside the cyclic host. Or this is trapped, the iron molecule is trapped inside the porphyrin ring. Similarly, the larger host molecules, they can also combine with the guest molecules. They undergo the crystallization process, just like that. The structure is just like similar to the structure of sodium chloride or NaCl. We can consider one will be a cation, another will be anion. It will be just like that. Okay. Or you can already discuss the type of semiconductor. You can check P-type semiconductor or N-type semiconductor. The structure will be just like equivalent. So here we can consider these are the larger molecules, host molecules, or throughout the complex or throughout the space lattice, there will be a huge number of host molecules, and the guest molecules they will trap inside some few number of host molecules, like that. So this type of overall complex is called inclusion complex or a host guest complex. Okay, or sometimes these are called the clathrate complex. These clathrates are particularly formed in noble gases. Sometimes the noble gases will form sometimes these types of structure. That means these noble gases they will particularly act like guest molecules. In the end of the class, I will show you how noble gases can form the clathrate compounds. Okay. And the third type of interaction is a assembling structure or aggregate structure, just like that. Small molecules, they will form a larger molecules, and the similar larger molecules, they will make interaction with themselves, and they will form just like a aggregate complex, like that. So here there will be no specific host, and there will be no specific guests. They just interact with themselves, and they will aggregate, and they will form just like a aggregate structure, like that. So there are three types of structures or three types of supramolecular complexes. So the host guest complex is typically, particularly, this is a enzyme substrate complex. They will form the host guest complexes. And lattice inclusion compound or clathrates, particularly gas species, occupy the cavities created by packing of host molecules in the solid states. These are created by the noble gas hydrates. Okay. So clathrate means just like bars. Okay. So again, self-assembly molecules means particularly the association of two or more molecules into larger aggregates directed by the instructions. So particularly the examples will be micelles, biological macromolecules. These are the example of self-assembly structures. So most of the synthetic receptors or molecular receptors are inspired by biological systems. So all type of or maximum type of supramolecular chemistry we are getting from the nature, or we are analyzing from the biological systems, or the artificial synthesis process. Actually, these are available in few amount, but we can observe most of the biological process. They can go through these types of supramolecular complexes, and particularly these types of supramolecular chemistry observed in enzyme interaction, antibody interaction, or nucleic acids, like that. Then some, particularly some of the few molecular receptors, earlier also, the crown ether complex, calixarene, cyclodextrin, and cucurbitryl, these types of complex. There are four types of complex you need to remember. So crown ether we already discussed. Yes, calixarene, all types of complexes already discussed. Particularly the last one, cucurbitryls. In this is a pumpkin seeds type structures, and in this complex, carbonyl ends will you can find out in the complex carbonyl ends, and this carbonyl ends, it will be absent in all types of molecular receptors. This will be always found in particular these types of molecular receptors. Okay. Then we'll discuss about their pre-organization of the molecular receptors, their enthalpy contributions, and the entropy contributions. So we can say that the pre-organized host has geometry that is already well suited for the guest binding, requiring little or no conformational change. So the pre-organized host, it should have a good geometry or proper cavity size to accommodate the guest. Okay. So the macrocyclic effect is to be considered here. Macrocyclic effect means just like crown ether complex. The crown ethers exhibits a stronger binding than the acyclic and analogous or codons. So definitely not the particularly crown ethers, any cyclic compound. They make a stronger binding comparing to the open chain compounds. So here also, that's why crown ether is a macrocyclic compound. They will make a stronger binding with the cation comparatively to the acyclic codon compounds, because their cyclic structure provides rigidity and pre-organization. So when we are taking a cyclic structure, it may be little bit flexible, but it gives idea about the proper cavity size. So when you are taking a guest molecule, if this cyclic ring, it will be little bit flexible, but it can accommodate this cation. Or if you take a little bit more cation also, sometimes they can accommodate inside the macrocyclic ring. But a open chain structure, it gives no idea about the interaction with the guest molecule. So particularly the codon molecules you can see here, these are the non-cyclic molecular receptors. They will not making a chain. They'll just making a forming a cyclic environment just like that, and at the end they are not connected. So the Podan molecules are the acyclic molecules. These are the acyclic molecules. Okay, or they are more flexible, so they must undergo conformational change to wrap against gas. So before gas interaction, they will just like bend like themselves within themselves to form a to make a cyclic structure like that. If you consider saying macrocycles, that means it is already organized, the rings are rigid, and they are making minimal entropy loss on binding. So after binding with the ligand or the macrocyclic ring, the entropy loss is very very less, and the binding tendency of the host and guest it will be much more strong. So the macro bicycles or cryptonoids. So sometimes you can take also cryptonoids. These complexes are called bicyclic complexes. You can see in the picture, figure 3.9. These are the foreign molecules. You can see bicycling. That means it's not forming a single cycle. In between the two atoms, they again forming a chain structure like that. That means this one will be one cycle and this one will be another cycle. That means this ring, this CH2, 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 this ring, just they will behave just like a bridging complex. And this bridging complex, if to a cyclic complex, a bridged complex will attach. They giving more rigidity to the ring. So if you compare crown ether with kryptonites, then definitely kryptonites favoring more rigidity due to the presence of ester, this bridging complex. So when the bridging complex is present, we can say this is a macrobicyclic ring. So in the kryptonite, the rigidity is more comparative to the crown ether also. Okay, we will come in. Already we have discussed here, macrobicyclics, even more rigid and pre-organized than macrocycles, provide three-dimensional binding cavity site. That means in microbicycles or kryptonites, the binding will be just like a three-dimensional binding. In three axis, we can see the binding of interaction. So if you are taking cyclic or cyclic ligand or macrocyclic ligands, this is just like a two-dimensional surface. But you are taking macrobicycles, it will provide three-dimensional binding cavities. So you know definitely that there will be three-dimensional binding site, then it will be more rigid. Just like in graphite and diamond. In, in graphite, they will form just like a benzene type of ring throughout the two-dimensional plane. But in diamond, the interaction will be just like a three-dimensional interaction. In X, Y, and Z, three axes, carbon is forming a single covalent bond with another carbon atoms. So when it will be a three-dimensional interaction, definitely it will be more stronger comparative to the two-dimensional interactions. So if you say a kryptonoid, crown ether, and the podans, whose rigidity will be more? Definitely kryptonite complex rigidity will be more, then thereafter crown ether, then thereafter podans. This is a podant structure. You can see it's not forming a cyclic complex like that. There will be these two ends, they are not connected to each other. So the podant complexes after interaction with the guest molecule, they make some conformational changes, they will form a stable complex like that. But the macrocycles here, and these four are the four ends for interaction with the guest molecules. They will form a complex like that. In both cases, stability arises after interaction, but in macrocyclic cases, the stability will be little bit more comparative to the codon structure. So if you check the enthalpic or entropic conditions. In Podan case, the negative entropy occurs due to conformational restrictions. Unfavorable enthalpy change occurs because the donor groups must be forced closely together, causing repulsions. So, in Podan complexes, these two terminal ends sometimes they will make some, or they will sometimes they will create some repulsion within themselves, and due to this repulsion, sometimes and there will be some negative entropy arises. And in macrocycles, a particularly lower energy entropy penalty because it needs no more randomness inside the structure. It's already a rigid or a stable structures. So here the entropy penalty is negative due to its restrict motion. Initially this is already in a stable form. So the macrocycles have lower entropy penalty. It's already rigid. So their donor groups pre-organized leads to the less entropy cost, and the donor side of the potents also are more solvated, more dissolution energy needed comparing to macrocycles. So when the ring will be little bit open, the chances of solvation is more. So when the ring will be little bit closed or just like a stable structure, the chances of solvation is very less. You can see in the structure a podant is fully solvated in solution. You can see in every end solvent molecules are connected with the podant structure. In macrocycles, in between the macrocycles, some few amounts of solvent molecules are present, so it is not fully solvated. You can see here. These things are mentioned here also. A podant is fully solvated in solution as it is flexible and the donor sites are easily accessible. And the macrocycles are often not fully solvated, as the solvent molecules would have to packed in close proximity in the center of the host. That means the solvent molecules they can only interact in the solvent center of the host. They cannot fully solvated throughout the structure of the macrocycles. So the solvation amount definitely it will be more important. The solvation amount it is less in macrocycles. We can take another example of zinc complex and a copper complex. So this zinc complex of the macrocyclic host. So the log K value 15.34 comparing to 11.25 for podants. So in case of M, if you are taking particularly the zinc atom, so here you are taking the zinc atom also, here you are taking the zinc atom also. This is a podant structure and this is a macrocyclic structure. You can check here for the macrocyclic, the K value or the stabilization constant value, it will be 15.34 and this will be less for the current. So the K value determines or gives idea about the stability of the complex. So if K will be more, definitely stability will be more. Okay. And the difference arises due to the favorable del H value and due to less unfavorable del S value. Okay. So one of the problem, particularly with the podant molecule, is that they are higher degree of flexibility. So due to the higher degree of flexibility, allowing them to adapt non-binding open conformation, or if the podant is terminated by a rigid functionality, definitely they will gain some extra stability, the organization inside the structure. So you can see here, so to make some rigidity or to gain rigidity of the podants, sometimes their terminal part, this part, they will connected with the larger groups or more steric groups. Then definitely the stability of the podant it will affect. So to make more stable the podant complex, sometimes the terminal group of the podants they will attach with the more steric group ligands or more steric groups. So the donor side of a macrocyclic are less accessible to a solvent molecules Then those of podants, as they are generally oriented towards the interior of the cavity. So this conformation prevents some solvent molecules from reaching them. That means solvent molecule, they cannot reach every donor site of the macrocycles because they are forming a rigid structure. But in case of podant, they are generally open type of structure, and the solvent molecule, they can interact with the interior part also and the exterior part of the cavity also. So we can say the podants can be fully solvated as they are flexible with their donor side and they can well separated. So when the podant binds to a guest molecule, more host-solvent interaction must be broken before the guest is able to bind. Therefore, a greater amount of energy is requiring for the binding to occur. So if you take a podant or along with a guest, so with a solvent, so initially there will be a host solvent and there will be a guest solvent complex. So when there will be interaction of host solvent and guest solvent, before this interaction, there must be need to breaking of the solvent host bonding. So if the solvent host, it will be more solvated before binding. We need then in this case we need much more energy to break them. So if in the case of podant solvent, in the case of macrocyclic solvent, and out of the two, this podant solvent they consume more solvent molecules. They will be more solvated. So in case of podant, we need much more energy to separate all the solvent molecules before the interactions. So in podant, you need to put, in case of formation of podant complex, you need to put a huge amount of energy for binding with the guest molecules. You can see the structure, sulfated structure of podant molecular receptor, sulfated structure of macrocyclic structure. Codon is fully solvated and is flexible, and the donor sites are easily accessible. Okay. Macrocycles are not fully solvated. A solvent molecules have to pack in close proximity in the center of the host. So the next step is that the macrocyclic effects we can take to one more step, further step to gain some rigidity further again inside the macrocyclic ligands. So the next complex we are going to discuss is macrobicyclics or cryptanoids. So cryptanoids they are forming a three-dimensional interaction with a guest, or it is more surrounded by the host, or I can say in a cryptanoid the guest molecule, which is the host molecule, it's just like the guest molecule. It will be surrounded by more number of donor atoms. But in macrocyclics, the number of donor atoms is less comparing to the cryptanoids. A simple structure of, you can see this is a cryptanoid structure. Now you can see this is a macrocyclic structure. So when there will be a cryptanoid structure, you can see the guest molecule. It will interact with the upper part also. It can interact with the lower part also. In this axis also, in this axis, in this axis. So in three axes, they can make interaction. That's why it is called three-dimensional binding in cryptanoids. But in crown ether complex, you can say in two-way or two direction or in two axis direction, the host and guest they can combine with themselves. So you can see here, this is a cryptanoid structure or macrobicyclic complex. This is called macrobicyclic complex that can interact with a guest molecule and they can form a three-dimensional interaction among themselves. So we can summarize or conclude that the pre-organization, if there will be a pre-organization, that can reduce the entropy penalty. The entropy will be less if the molecular receptor is more pre-organized. So next thing is that next other factors that can affect the molecular receptors activity, minimizing the conformational rearrangement. So if you initially you are taking a flexible pre-organized host exists in a variety of disorder conformations in solution. Upon binding a guest, it must adopt a specific or rigid conformation. So this loss of conformational freedom occurs a larger entropy penalty. That means when a host and guest they will combine and the host will undergo through a huge amount of conformational change. Then in this case, we can say it will lose a higher entropic penalty. But if initially you are taking a pre-organized host, then the entropic cost and the entropic penalty will be less. So the initial complex or initial host molecule, if it will be more pre-organized, then you need to say that the entropy cost will be less. If the initial host molecules pre-organized nature or pre-organized amount is very very less, then you need to observe a larger entropy penalty. So this is called entropic prepayment also. So by building the receptor with a rigid framework, the synthesis process creates the entropic penalty associated with the freezing out the rotational and conformational freedom. So this is sometimes referred to as the entropic prepayment or the final binding event, therefore carries a much smaller entropic cost. So reduce the dissolution penalty. So when a receptor and a guest bind in aqueous solution, they displace ordered water molecules from their surface, leading to increase in solvent entropy that can favor binding. So if you are taking a suppose in you can say if you are taking NaCl salt, you can add in water. Then after some time, the Na plus and Cl minus ions they will be completely separated, and the Na plus ions they will surrounded by the OH minus ions, and the Cl minus ions they will surrounded by the H plus ions. So if the separation will be more, we can say there will be a increase in solvent entropy. Okay, that can form a more stable complex. So, however, the initial dissolution of a non-pre-organized host binding site can also be energetically unfavorable. So, if you are taking a pre-organized source, then it will be energetically favorable. But if you are taking a on-pre-organized source, that means you need to put some input energy, which is energetically unfavorable. So, by designing a pre-organized and complementary binding set, the dissolution process it can be minimized, contributing to a more overall binding cleavage. So by enhancing chelate or microcyclic effect, this principle we can make a more stable supramolecular complex. And further we will going to discuss about the chelate effects. So chelate effect means the ligand must be a multidentate ligand or it must be a polydentate ligand. It must have more than one binding site. Okay, or it is forming a more strongly complexes comparing to the similar equivalent monodental ligands. This is larger because in solution, chelating ligands particularly, it is a more number of binding sites and proximity, and it can reduces the entropic cost and bringing the multiple ligands into the proper position that can coordinate with the metal atom. Okay, so simply you can say you are taking cobalt Cl6 3 minus complex and you are taking cobalt En3 3 plus complex. Then in both cases, the donor atoms are similar, or we can say the donor sites are similar. There are also six ligands, 6 donor sites are present. Here also 6 donor sites are present. But the difference is that the environment of the ligand. In chelating ligand, they make different environment. They make a cyclic environment. Okay. And you can take also macrocyclic effects. Macrocyclic effects, I can already told you the chronoether complexes, cryptanoids, they can form macrocyclic effects, but the linear chains, codon structure, they cannot form a macrocyclic effect. This is because macrocyclic is pre-organized. Initially, macrocyclic is pre-organized, but the codons they are not organized. Next, we will discuss about the binding constants. What will be the binding constant or what will be the equilibrium constants? Particularly, what is binding constants? That is mentioned here. The equilibrium constants for the interaction or after the interaction of a host with one or more guest molecules. So the binding constant provides a quantitative representation of degree of association, is also called also the association constant. So if the binding constant will be more, binding constant or K value will be more, we can say the stability of the complex is also more. So when we are adding or when we are taking a aggregated complex, that means few molecules they can be added just like one by one. So in first adding process, we need to observe the binding constant. In the first step, if you are adding the second molecule, we need to observe the second compound's binding constant like that. And the overall constant, this is if you calculate the overall binding constant, you can simply say this is the overall constant. Okay. Here we will show you one by one what is binding constant value and what is the these are the stepwise binding constants. And the final one will be the overall constant. So first we need to check their definitions and their theoretical expressions. The binding of a guest molecule with a host or the interaction between two or more species, it occurs through particularly non-covalent forces. And this interaction, this is also equilibrium constants. That means the host and guest they can combine also, and on a favorable condition, they can also separate it to form a just like an initial reactant. So the strength of this binding is expressed by the binding constant. If the binding constant value is more, that means the host guest binding uh, factor will be more, the strength of in between the host and guest. So for simple one host and one guest, we are taking one host molecule and one guest molecule, the equilibrium can be written as below, just like here. Host and guest, and this is called host guest complex. So we can say the equilibrium constant value it will be the concentration of host guest divided by the concentration of individual host and the concentration of individual guests. So this is the mathematical expression for determining the equilibrium constant value. If if you combine one host molecule with one guest molecule. So the binding constant K is calculated using the equilibrium constant of the key host, the guest, and the host system. So the binding constant will be more inverse decimal two or over there. So there is expressed sometimes in logarithm also. So in practice, binding constant value that can be determined experimentally. So some are the spectroscopical techniques you can use to determine the binding constants. One is NMR spectroscopy, or you can use UV visible absorption spectroscopy, or you can use fluorescence spectroscopy. So these experiments particularly provide data about the position of the equilibrium from which K can be calculated. So frequently, post-test complex load form extremely straightforward 1:1 ratio. In such cases, there is much more than one binding constant. Sometimes there will be subsequent guest molecules that can bind to the host molecule. Because a host they can have also one active site. Sometimes they can have also multiple active sites. So a host they can accommodate one or guest molecule more than one guest molecules. So sometimes multiple equilibrium can exist, which can be in monomer dimer complex. In second step, they are forming a trimer complex like that. And the overall binding constant or the overall binding constant of the final product, it can be determined by term overall binding constant. This is called beta. So I will show you what is stepwise formation constant. So this K1, K2, K3, these are the stepwise formation constant. You can see here, initially we are taking one mole host and one mole guest, they are forming Hg like that. And further, this Hg molecule, they will added by another guest molecule, they will forming the complex like that. So here the equilibrium constant value it will be K2. And further, this Hg2 it will be added by G. Here there is a printing mistake. This is not Hg, this will be H dot G2. It will be added by G, it will forming a Hg3. Okay, so this one K1, K2, and K3. So these are the stepwise formation constants. But if you say in a single sentence or a single equation, host it can combine with three guest, it is forming Hg3. and the equilibrium constant value will be B3. So here this B3 is called overall binding constants, and this K1, K2, and K3, this will be the stepwise binding constants. So there is a popular relationship that is exists in between the overall binding constant and the stepwise formation constants. So B3 value, it will be always, it's a multiplication of K1, K2, and K3. Okay. So here also you can multiply these three terms K1, K2, K3. You can multiply also if you are multiplying this one, and this one. Finally, you are getting this. So you can cancel out this one. Okay. We are taking K1 multiplication of K2 with multiplication of K3. You can see here this SG will be cancelled out, and here this G molecules, it will be cancelled out by this G also. Okay, and this Hg3, you can cancel this one also. Okay, so finally you can get three G molecules, G, this one, Hg. Okay, and finally you can get this 3G. This 3G will be multiplied. This will be converted to GQ. There will be one H, and the above one will be this one. So you can mathematically you can check also. You can take the multiplication of K1, K2, K3, and you can finally got this values already. HGGG. It will be HGQ, and the above one will be HGP. Okay. So you can remember this expression. If you are taking B3, it will be a multiplication of K1, K2, K3. If you are taking B4, it will be obviously like that K1, K2, K3, and K4. Okay. So always the overall constant, overall binding constant value, it will be more than the stepwise formation constant values. So you can derive a relationship in between a stepwise and overall binding constants just like that. Okay, so these are thermodynamic parameters for the gene complex of 3.5A and 3.5B. You can check here. This one, 3.5A. B will be the macrocyclic complex, and this one will be the acyclic codon complex. Okay. So this K value, this overall constant K value, we are calculating for the 3.45A complex and 3.5B complex. So in case of 3.5A, the K value will be log K value will be less. In case of macrocyclic complex, the log K value will be more. You can see here also the del S value will be negative minus 44.4 negative for the codon complex, and here also it's negative, but it's more negative. So if minus del H or enthalpy will be more, then the reaction will be more feasible. Here we can check also minus T del S, it will be less negative here, and here it is more negative. So you know that for feasibility of the process, you know, just like that del G, it will be equal to del H minus T del S. So if del G will be more negative, the reaction will be more feasible, and the reaction will be more spontaneous, or the stability will be more. So you can see here already minus del S value will be more for the macrocyclic effect, or you can say this T del S value, it will be less, a little bit more negative for the macrocyclic effect. But by this difference, you can see, or by comparing the simple del S value, we can see here for macrocyclic effect, the enthalpy will be more negative. If this del S value will be more negative, del G will be more negative. Okay, so this reaction will be more feasible. So this is a comparison between the codon and macrocyclic complex, not a macro bicyclic complex. Okay. So here we are comparing three complexes. One is podant, one is podant, or this is a macrocyclic cyclic complex. This is a podant complex. This is kryptonite or macrobicyclic effect. You can see here the structures. The podant structure is just like a open chain structure, and it will be make a little bit organized structure, but this is still it has more flexibility. If you're taking a cyclic structure, that means the nature of organization is increased, or nature of the pre-organized nature of the host molecule, it will be increased. If you're taking the kryptonite, the pre-organized nature, it will be highest here. So from up to down, you can see here the organization amount or degree of organization, it will gradually increases. So out of these three complex, you can say the kryptoniotes or macrobicyclics has more stability. Thereafter crown ether, thereafter podant. So this is a comparison of these three types of structure. Okay. So you can draw also in exam. If they will ask question, you can simply draw it and show them. Okay. And this is the example of another types of kryptonite or macrobicyclic complex. We are taking the potassium ion and they will get trapped inside this kryptonite. Okay. So one of the major issue in kryptonite is that there are a lot of number of donor atoms are present. If the lot of number of donor atoms are present, sometimes the lone pair in between the donor atoms, they will cause some repulsion within themselves. So this due to this repulsion, the kryptonite complexes sometimes they will lose its some few amount of stability. Okay. So kryptonite complex, definitely these are stable, but sometimes their stability will be also little bit decreases due to the repulsion in between the donor atoms, or the repulsion in between the intracavity lone pairs. Okay, just like that. Here, this is a oxygen atom present. Here, this is oxygen atom present. So this oxygen atom's lone pair, it can repel this oxygen's lone pair. This nitrogen's lone pair. This can also repel this lone pair of oxygen, like that. Or you can see here the simple structure. This oxygen lone pair and this oxygen lone pair, they can make a repulsion in between them. So these types of repulsion also increases or also available in crown ether complex also. But in podant, particularly the donor atom is the number of donor atom is much more comparing the crown ether. Okay. So in podant, sorry, in kryptonite, the number of donor atom is much more higher. So here the lone pair repulsion, it will just like much more high. Here the number of donor atoms also decreases. But still the donor atoms, they are possessing the lone pairs, they can make repulsion in between themselves. So this is micro bicyclic and this is macro cyclic. But the benefit of the podant structure is that they are non-cyclic complexes and their donor atoms, they will remain far away from each other. So they will feel less repulsion. Or if in a ring also, when they will form a cyclic ring also, if they feel repulsion also, they are generally flexible in nature. They can change their conformational change, or they can form a stable complex. So this is one benefit of the podant comparing to the macrocyclics and macrobicyclics. Next, we will discuss about the complementary. Okay, so when the term complementary arises, and then particularly we need to check the structural complementary and chemical complementarity. So structural means size and shape of the cavity must match with the guest, and chemical complementarity, just like previously I told you, the non-covalent interactions. So along with the non-covalent interaction, there will be another factor. Previously, I told you hard soft acid base theory. That means hard metal, it will prefer to bind with the hard donor side, and the soft metal it will prefer to bind with the soft ligands. That's why in crown ether complex they can trap only the hard metals, just like Na plus, potassium plus, cesium plus. Okay. If the in case of oxygen donor, if you can take the nitrogen donor, they easily trap the transition metals. Okay. So according to Donald Trump, complementary means host master binding site which cooperatively contact and attract the binding site of guests without generating strong non-bonded repulsions. Okay, that means binding tendency in between the host guest it will be stronger. Along with there will be no repulsion among within themselves or within the donor atoms. Okay. So this is an example of the hard acid and hard base interactions. So K plus this is a hard metal in crown 6, 18 crown 6 complex. It is make a non-covalent interaction with the 6 oxygen atoms. And these oxygens, these are the hard bases. So the substitution with the soft donor, it can reduces the binding. If in place of oxygen, nitrogen is present, they cannot strongly bind the K plus ions or the hard metals. You can see here, these are the codon structure, these are the crown ether complex structure, these are the cryptanoid structure, this is pyramid structure. Okay. So along from left to right, when we will go, they will be more pre-organized. That means rigidity will be increases when you go from left to right. This is a open structure, this is a closed structure, this will be bicyclic structure, and here the benzene rings and side substitute groups are also attached. So here the rigidity will be more. But in all cases, most of the cases, the donor atom is oxygen. So they can accommodate the hard metals or hard acids. Here you can check here diaza 18 crown 6 complex, and you can take Lariand ether complex. Okay. So here the K value it will be 2.04, and then here the K value it will be 4.8. Okay. So the Acha macro cycles, this complex, it will be less complementary for the K plus ion atom. And this one will be suitable for the K plus atom. So these are the terminal questions you can discuss or write in your notebooks also. A receptor designed for binding urea derivatives contain multiple hydrogen bond donor groups, particularly, and in urea NH2 group is present. So when there will be NH2 end, so particularly nitrogen, they can make interaction with the other urea molecules, hydrogen atom, they can form hydrogen bonds. So in answer, there may be some picture. Okay, there no picture. Okay, a receptor designed to bind urea derivatives contain multiple hydrogen bond donor groups because of the principle of cooperativity and the need for high binding affinity and selectivity. So in urea molecules within themselves, they can bind, they can form multiple hydrogen bond interactions. So discuss the importance of rigidity and flexibility in the design of synthetic receptor. I already told you we are taking the comparison of three compounds. One is podant, another is ground ether, another is kryptonite also. Okay. So when you are taking the podant molecules, no doubt, this is an open chain structure. The rigidity is less, but flexibility is more. So when the flexibility will be more, there will be less electronic repulsion in between the donor atoms. So if you compare the flexibility, then definitely it will be more important comparing to the crown ether and kryptonite complex. So when we will discuss about the rigidity, It will gradually increases from codon to crown ether and again from crown ether to kryptonite, like that. Okay. So how does reorganizes reduces the enthalpy penalty? So when the host molecule initially it will be more pre-organized. So after interaction with the guest molecule, it doesn't increase the randomness inside the system because it initially the host molecule is a stable complex. So the entropy cost will be less if the pre-organization nature of the host molecule it will be more. And enthalpy driven and entropic driven already I am discussed here also. If the del H value will be more negative, del G will be more negative, reaction will be feasible. If I say about the entropy cost, if the entropy cost or del S value will be more positive, then del G will be negative. So for a feasible process, it will be better if the enthalpy will be more negative or the entropy will be more positive. Okay, so explain the role of pre-organization in minimizing conformational entropy loss upon complexation. You can check here the answer also. The pre-organization minimizes the conformational entropy loss during complexation by ensuring that a receptor is already or near its ideal binding conformation. So when I am saying pre-organized structure, that means the receptors is already making a good binding site for the guest molecules before the guest molecule arrives. A flexible host conversely must conturn into a specific set to bind its guest. So this ordering of a disordered state indicates a significant entropic penalty. So P-organization particularly reduces the entropy cost. So entropic prepayment during synthesis. So for a flexible molecule like codon, there is a high entropy cost. But for a more pre-organized and rigid structure, the entropy cost is very, very less. And other things also, you can give example in organized or pre-organized structure or for conformational and non-conformational changes, lock and key theory, induced fit theory, I already discussed previously. So for lock and key theory, there must be a rigid substrate complex that is making a proper cavity size and a key will come, they will just fit inside the substrate. But in induced fit structure, these types of things will not happen. Initially, the guest molecule it will interact with the host molecule. Thereafter, according to guest molecule, the host molecule make a changes in their conformational structure. Thereafter, a guest molecule can fit inside it. But in lock and key theory, after interaction of guest molecule, host molecule doesn't change its conformational structure. So these are the basic things. You can discuss one by one. And here are some other supramolecular things. Supramolecular devices, supramolecular catalysts, all are important. Self-assembly. The meaning of self-assembly means recognition between the molecules leads to aggregation structure, which finally results into a discrete unit sometimes also. So when there will be self-assembly structure, there will be two chances: strict self-assembly or directed or template self-assembly. So strict self-assembly directly proceeds towards the formation of well-defined aggregate. Or if I say directed self-assembly, that is controlled or influenced by some additional species. This means you can see here an idealized case of self-assembly follow a cooperative effect or a allotropic effect. That means when you are adding a guest and host, then definitely there will be chances to form a stable complex. But in directed self-assembly, that will occurs by stepwise manner. Just like in hemoglobin, you are adding one molecule of oxygen, it will make a environment or it is make a supporting environment for addition of another oxygen molecules. Then the second addition of oxygen molecule, they will make a favorable environment to add for adding of third molecules. But in strict self-assembly, the stepwise manner interaction doesn't occur directly. They will combine the host and waste molecules. They will directly combine with each other. Okay. So another is that supramolecular assembly or Fuji interactions. So the Fuji interactions are the sometimes the unclear interactions. Sometimes they will be more flexible, sensitive, and adaptability functionality, just like cell membranes. So if I say cell membranes, and so cell membrane or particularly potential membrane, they will just act like a different condition. They will make different condition according to their concentration. You know about exosmosis or endosmosis. If you make a concentrational change outside the surface, then the flow of the molecular movement it will be different, just like that. So it will sometimes it will depends upon the particularly the adaptable functionality. That means the particular environment. Okay, you can see supramolecular self-assembly compound like that. We're adding the guest molecule, and the guest molecule go inside of the cavity of the solvent host, and you can see the water molecule just moving outside. So sometimes we can say programmed supramolecular assembly. Programmed supramolecular assembly, they are particularly defined about the artificial DNA synthesis. That means in a systematic manner, we are putting the amino acids. So if the amino acids sequence will change, definitely the protein structure will change. So you know in DNA particularly, the combination is just like AT adenine. It can combine with thymine, guanine. It can combine with cytosine, just like that. So this is just like a program, self-programmed in nature also. So in DNA, you can see here this particular acid, amino acid, this can combine with this particular amino acid of this another strand. You can see here thymine, it can only combine with adenine by two hydrogen bonding. And in cytosine, they can combine it with guanine by making three particular hydrogen bonding. So this is just like a programmed manner. This is nature's programming, but now scientists artificially they can also making proteins by in a manner of programming order of by supplying a programming order of amino acids also. So this combination always favored just like a programming nature. Like thymine never combine with guanine or cytosine. Okay, just like that. So for this programming nature, hydrogen bonding is also necessary. This is also a type of non-covalent interaction. So within thymine and adenine, always two hydrogen bond exist, and within cytosine and guanine, three hydrogen bonds exist. So you can say in both cases, in which cases the strength is more. We can say the number of hydrogen is more here, and the strength will be more in cytosine and guanine. Okay, so this is a structure of lipid bilayer, and these big structures are the protein molecules that present inside the lipid. Bilayer means this is one layer and this one will be another layer. And the circular balls are the hydrophilic ends, and the straight lines are the hydrophobic parts. So our skin, or I can say the lipid bilayers, they contain both environment. So one of the part will be hydrophilic and another part will be hydrophobic. So you can see here the hydrophobic part makes interaction with the hydrophobic part here. That's why this is called lipid bilayer. The two layers are present, and the circle part is the hydrophilic part, and the straight line part is the hydrophobic part. So sometimes this is called the amphiphilic. That means they contain both hydrophilic part also, they contain both hydrophobic tails also. Okay, so in graduation also, micelles also they are also forming the structure like that. They have a hydrophilic end also. They have a hydrophobic part also. Okay. Again, you can see in the center the hydrophobic part is concentrated. Or straight lines are concentrated. If again the hydrophilic ends, they will merge at the center part. They will form a structure like that. Then the aqueous solution, the micelle formation looks like that. If you take any organic solution or non-polar solvents, then the structure will be just like that. Here we can say the center part will be the hydrophilic environment, providing hydrophobic. So in this structure, you can see here in both of the in both the host molecules, the potassium ions they can accounted. Here also the potassium ion can accounted inside the structure. Here also the potassium ions they can trap inside the structure. But here the binding constant value is 10 to the power 6, and here the binding constant is 10 to the power 10 because this is kryptonoid. They are offering three-side interaction or three-dimensional donor atoms. Means in this direction also they can combine with this oxygen, oxygen, nitrogen, nitrogen, and in here also in upper of the plane, these two oxygen atoms they can also bind with the potassium ion. So this is a two-dimensional surface. This providing the two-dimensional surface to binding with the potassium ion, and here it provides three-dimensional surface binding with the potassium ion. Okay, or simply I can say here that the effect is macrocyclic effect. This is macro bicyclic effect. You can see here also the lithium that can accommodate sodium also, that can accommodate potassium also. Okay. So here with increase in size, the specific cavity or the specific host also increases. So this lithium, this is suitable for this complex host, and this sodium, this will be suitable for this one, and this potassium, this will be suitable for this particular host. Not only the binding sites, along with the cavity size is also important parameter for stability of host-guest complex. So supramolecular devices. So these are the molecules or assemblies that can perform functions such as sometimes a linear rotational motion, sometimes switching, sometimes entrapment, or this device exists at the boundary between supramolecular chemist or nanotechnology. Course that can be demonstrated by using the supramolecular concepts. So the supramolecular compounds sometimes they can behave like molecular photonic device that can recognize or that can sense the light emission or absorption process. This is called molecular photonic devices. Or sometimes they can use just like a molecular electronic devices. So I can show you one example. This is a structure of molecular photonic devices. So if you take dimolar dimor naphthalene formation, this results in a strong emission. So inclusion of a guest inside this cavity is induces the light emissions. So these two naphthalene molecules, when they will get trapped inside a host molecule, they will emit light. Okay. So if someone wants to induces, if someone wants to restrict the light emission process, they can add another guest molecule, and in presence of the host and guest interaction, now the naphthalene dimer they cannot emit light more strong. Here also you can see. So the light here also another fundamental method follows. Here light emission occurs after the binding of the potassium ion to a crown ether. So initially this crown ether complex they are not forming a or not emitting the light, or they behave just like a quenching process. But if you add a potassium ion, and after the addition of the potassium ion with the particular host molecule, now it is emitting light. So we can say sometimes we can induce the photon reactions by adding or by making host-guest interactions. So before it will behave just like a quenching process, and after addition of potassium ion, now it is emitting light. So this is called molecular photonic devices. These are called molecular photonic devices, and these are called molecular wires also. So the molecular wire it is just like a lipid bilayer. Okay. So initially the electron flow doesn't occur inside the molecule, but after addition of this guest molecule, now the electron flow it can occur throughout the lipid bilayer. Okay. Sometimes these are called also switched process or photoregulated process. That means, particularly, we can say the host guest interaction that can affect the photonic processes, or they can sense the observation of photons, they can emit light, they can absorb light, okay, like that. So, these are the process, that's why this is called molecular, supramolecular devices. Sometimes some supramolecular complex behavior, this is called like supramolecular devices. Okay, so if you have any doubt, you can ask. Okay, thank you everyone.
Thank you, sir.